Here we're going to solve a natural abundance isotope question. So we have silver, and it has two naturally occurring isotopes. We have silver 107 with atomic mass of 106.9051 AMU, and 109 silver with an atomic mass of 108.9048 AMU. So if the atomic weight of silver given on the periodic table is 107.87 AMU, what is the natural abundance of both isotopes? This is your clue that this is a two equations with two unknowns question. So what we have to do is figure out what our two equations are going to be. In the first case, because silver has two naturally occurring isotopes, I'm going to set my x equal to the natural abundance of silver 107 as a decimal. Y is then going to be equal to the natural abundance of silver 109 as a decimal. So these are my natural abundances as a decimal. Now that I have my two unknowns defined, we have to come up with our two equations. The natural abundance of both of them when added together will equal the atomic weight. The atomic weight on the periodic table is the weighted average of all of the naturally occurring isotopes. So this is going to be the answer to one of our equations. So we're going to take the atomic mass of silver 107, so 106.9051. Keep all of those units with you as we go along. That's going to be multiplied by the natural abundance as a decimal of silver 107, plus the atomic mass of silver 109, 108.9048, times the natural abundance of silver 109 as a decimal, that's Y. That weighted average, when you add them together, will give you that atomic weight, the atomic weight from the periodic table for silver, 107.87. That's our first equation. Our next equation is we have to have 100%. X plus Y must equal 1, because that's the definition of sort of what's going on with these things. We only have two isotopes. When you add them together, they must equal 100%. So that's our second equation. Now again, if you get to this point, you're more than halfway there. The rest is just math. So let me step you through solving the math of this. So the first thing I'm going to do is solve my second equation for one of my variables. So I'm going to solve for y. In order to isolate y, I'm going to subtract x from both sides. And in the end, what you get out is y equals 1 minus x. Could have solved for x. X equals 1 minus y. It doesn't matter. All that matters is that you solve for one of them. And now I'm going to take this and plug it into my first equation wherever y shows up. Y only shows up there. So we get 106.9051 times x plus 108.9048 times y, where y is equal to 1 minus x, equals 107.87. Now I'm going to distribute that 108.9048. I keep 106.9051 x plus 108.9048 minus 108.9048 x equals 107.87. From here on, all we're trying to do is isolate x. So we've got x over here and x over here, so they're both on the left-hand side of the equation. We're just going to keep those together and solve for it. So now, in order to isolate it, I am going to subtract 108.9048 from both sides. I'm going to keep my 106.9051x minus 108.9048x, and that is equal to negative 1.0348. At this point in time, you might be panicking a little bit. That negative sign is going to end up taking care of itself. Don't lose it. It's important. So what I'm going to do now is I'm going to do this math over here. I'm just going to subtract those two values. So you can see that a 106 minus 108 should give me a negative number. And so indeed I get negative 1.9997. X equals negative 1.0348. See, the negative signs are going to take care of themselves. In order to isolate x, I'm going to divide both sides by negative 1.9997. So what I get out in the end is x equals 0.51748. So you might be asking, how did you know how many significant figures to use? Right up here was given to us the atomic weight of the silver from the periodic table, and it has 1, 2, 3, 4, 5 significant digits. So I'm going to keep 5 significant digits down here. The other numbers given to us in the question had more than 5, so I'm going to go with the least. So this is equal to 51.748%, and we defined our x to be the natural abundance of silver 107. You can look back up in here. You can see I defined x as the natural abundance of silver 107. So that's the natural abundance of one of our isotopes. The natural abundance of our other isotope is going to be 100, because again they equal 100%, minus 51.748 gives us 48.252% silver 109. And it's interesting in this case that we have a roughly 50-50 mixture of these two isotopes. And that should make sense to us. We have 107 and 109, and the atomic mass, atomic weight that we were given on the periodic table is roughly halfway in between. It's a little bit closer to that of 107. That's why we have just a little bit more of the silver 107. So there are natural abundance of both of those isotopes.